In this video, we discuss f of x equals the natural log of the square root of 1 plus sine squared. We always like to talk about the domain of a function before we start doing anything with it. Now, in the problem statement in the book, I think they ask us to find the tangent line at a particular x value. I think that x value is pi over 4. But I'm actually interested in the graph just in general. We know that the domain of the logarithmic function is all x values, such that the argument, that's what's inside the logarithm, is greater than 0. But that square root is always positive. The square root of anything is always positive. So that's going to be well defined as long as 1 plus x squared is, or 1 plus sine of squared x is positive, right? Now think about sine of x. Sine of x is always between -1 and 1. So when I square, or excuse me, yes. So when I square it, the y values are always going to be between 0 and 1. Because the minimum that this squared number could be is 0, and the maximum that could be would be when we square -1 or when we square +1 and we get +1. So this is between 0 and 1, and then we add 1 to it. So this is actually greater than 0 all of the time. It doesn't matter what x is, because this number is greater than or equal to 0. This is always between 0 and 1. When we add 1, this sum is always between 1 and 2. So we're actually taking the square root of a number between 1 and 2, and then we're taking the log of that. The logarithm of 1 is 0, so the minimum value of this function should be 0. And the maximum value of this function should occur at when this expression is 1. So when we have the natural log of the square root of 2. Alternatively, we could take that square root and write it as a 1/2 power. If you've got natural log of a to the n, you can bring that n in front. So this is actually the same as 1/2 of natural log of 1 plus sine squared x. Now, typically I would say, be careful though, because the domain of this might not be the domain of that, but this time we're fine, because here we're just taking the square root of a number between 1 and 2. And now when we put that 1/2 out front, now we're just taking the logarithm of a number between 1 and 2, and then we're multiplying by 1/2. And those y values are going to be exactly the same because of those identities, because of this particular identity, natural log of a to the n equals n times natural log of a. So the domain of f is this, but this turns out to be true all the time, because this is always between 1 and 2. So our domain for the function is actually all real numbers. And if I want to, I can graph that y equals 1 plus sine squared x. This will equal 1 whenever sine squared x is 0. And sine squared x is 0 at 0, pi, 2 pi, 3 pi. So our y value is going to be 1 here, and here, and here, and here. And at pi over 2 and 3 pi over 2, sine of x would have been +1 at pi over 2 and -1 at 3 pi over 2. But then we square it. So we're going to get 1 squared here, which is 1, plus 1 is 2. And then here we're going to have -1 squared, which is 1, plus 1 is 2. And then here we'll have +1 squared, which is 1, plus 1 is 2. And so our graph is going to look roughly like this. I'm not really sure about sort of the concavity and everything in between, but roughly that's what our graph will look like, just for that expression under the radical. So we're taking the log of these numbers that are between 1 and 2, and the logarithm of 1 is 0. So we're going to get the logarithm graph is going to equal 0 when all of these y values are 1. We'll get a 0 here, and a 0 here, and a 0 here, and a 0 here. And then at these x values, when this function is 2, we're going to have the natural log of 2, which is about that 0.69 or 0.7-ish times 1/2. So it's about 0.35. So this function should look roughly like this. All right, so that's our function. Now we were asked to find the tangent line at a particular location. So let's graph or let's find the derivative and then graph it. The derivative of 1/2 of the natural log of a function is 1/2 times 1 over the inside function. And that sine of x, sine squared x is actually sine of x quantity squared. So when you take the derivative of that, you're going to use the chain rule because you've got a function inside that squaring function. So the derivative of that denominator is derivative of 1, which is 0, plus the derivative of function squared. So that's going to give us 2 times that inside function, which is sine of x, times the derivative of the inside, which is cosine of x. And that 1/2 and that 2 reduce. So what you end up with is f prime equals sine of x times cosine of x, all divided by 1 plus sine squared x. So I've got sine times cosine, and then I've got this 1 plus sine squared x in the denominator. That is, so I'm dividing this expression by a number between 1 and 2 again. And this sine times cosine is actually 1/2 of sine of 2x. So if you want, you can write that as 1/2 of sine of 2x. And then we can see that the period is actually going to be, instead of being 2 pi, our period will be, the period of this function is pi. So every pi units this repeats. And then we divide by this 1 plus sine squared, which is dividing by a number between 1 and 2. All right, so that's our f prime. Now if we wanted to, we could find out when f prime equals 0 and look for relative extrema. This is equal to 0 whenever 2x is a multiple of pi. So that's n pi when n is an integer. So whenever x is equal to n pi divided by 2. So all of the multiples of pi over 2. So that's going to be pi over 2, pi, 3 pi over 2, 2 pi. It's pretty much all the time. And then we can think about when sine of 2x changes signs. Sine of 2x looks a lot like sine of x. It looks like that. But the period, instead of being 2 pi, is 2 pi divided by that coefficient of x. So it's pi. So it's equal to 0 at half of the period. It has that max at 1/4 of the period. And then this is 3/4 of the period. So f prime is equal to this fraction. It's equal to 0 at 0 and pi over 2 and pi and so on. But then it changes signs when the sine of 2x changes signs. So if we're looking at f prime on a number line, and I'm just graphing some of those multiples of pi over 2. From 0 to pi over 2, the sign is positive. Then from pi over 2 to pi, it's going to be negative. Then it's going to be positive, negative, positive, negative, and that pattern repeats over and over again. So we're going to have a function that's increasing, and then it has a 0 slope, and then it's decreasing. And then it's decreasing, it has a 0 slope, and then it's increasing. And then it's increasing, it has a 0 slope, and it's decreasing. And it's going to keep going like that. And that's what we see here when we look at that graph there. We've got minimums at 0, pi, 2 pi, 3 pi, which is what we see on this chart. And then at all the multiples of pi over 2, or the odd multiples of pi over 2, we've got a max at pi over 2, 3 pi over 2, 5 pi over 2, and so on. So the function has a relative max at odd multiples of pi over 2. And the function value there is, well, it's 1/2 of natural log of 1 plus sine of that odd multiple of pi over 2 squared. And at that odd multiple of pi over 2, sine is either going to be -1 or 1. So we're going to take -1 or 1 squared, we're going to get 1. 1 plus 1 is 2. And so we get 1/2 natural log of 2, which is what we talked about already. It's about 0.35-ish. It's 0.69 divided by 2. And then our function has a relative min, or has many relative min, when x is equal to pi n, and an integer. At that pi n, the sine squared is going to be 0. So this is 0. So we have natural log of 1, which is 0, times 1/2, which is 0. So the function values are 0, which is what we see on the original graph. So we were able to infer all of that even without taking the first derivative. We could compute the second derivative, but I don't think it's going to be that insightful, honestly, but just tell us something about the concavity of this. But let's look at these graphs on Desmos, and then let's find the equation of the tangent line at pi over 4. I believe that's what we were asked to do in the textbook when we were given this function. I was just interested in this problem because it had this pretty function in it. So here's that function I mentioned, 1 plus sine squared x. We said that the y values were between 1 and 2. And I think that we can see that. So let's zoom in. Let's let our y values go between -2 and 3. And so we see the y values are between 1 and 2. Oops. Maybe I will use step size of pi over 4 for our pi values. Well, it didn't label that properly. But then we're taking the square root of that number. So we're taking values between 1 and square root of 2, and then we're taking the natural log of that. Or alternatively, you could just put a 1 plus sine squared x inside the function, the logarithmic function, and put the 1/2 out front. I prefer to look at it that way. So we're looking at values between natural log of 1, which is 0, and natural log of 2, which is that 0.69, and then we're multiplying them all by 1/2. So instead of going from 0 to 0.69, we're going from 0 to half of 0.69. So it's about 0.35. So that's our function. And then we computed the derivative. And we said that that was sine of 2x divided by 2 times 1 plus sine squared x. Looks a little bit wonky, doesn't it? So when was that derivative equal to 0? Well, it's equal to 0 at 0, pi over 2, pi, 3 pi over 2, 2 pi, and so on. And the derivative is going from negative to 0 to positive at this 0, and then positive to 0 to negative here. So this one corresponds to a relative min because the function is decreasing, then it's 0, and then it's increasing. So it goes from decreasing to having a 0 slope to increasing. And then at this 0, the function goes from increasing, because the derivative is positive, to having a 0 slope to decreasing. So you had a relative min there and a relative max there. And now if we want to, we can graph the tangent line at pi over 4. So we'll say this is equal to y at pi over, or y equals the y value at pi over 4 plus the slope at pi over 4 times x minus pi over 4. Looks like that. Then we can graph that point at pi over 4. We see that has the same slope as the original function. And if we want to, we can change that to an x value that that varies. I like doing that. So now we can move this point around and we can see how the tangent line changes from point to point. And if we want to, we can also graph the derivative function and look at the derivative at that x value. So I know the slope of this tangent line is 0.314 there. The tangent line at the top should have a slope of 0 approximately. And that when I evaluate the derivative there, I get something that's very close to 0. Tangent line at the bottom should have a slope of 0. And we see that it does. And that's how it goes. It repeats every pi units. We had a 0 there. And it continues. So again, the teal graph is the derivative, and the orange graph is our original function. And that purple line is our tangent line. And that other sort of floating purple dot is the derivative value. Okay. So maybe we are interested in points of inflection. I'm a little bit curious. Aren't you a little curious about points of inflection? I am. So let's compute the second derivative. So according to the quotient rule, you're going to get a quotient. It's low, d high. And the derivative of sine of 2x is cosine of the inside function times the derivative of the inside. And the derivative of 2x is just a 2, so I'm going to multiply by an extra 2, so I'm going to get a 4 out front. Minus high, and sine of 2x, d low, is 2 times the derivative of 1, which is 0, plus the derivative of sine squared x. So that's sine of x quantity squared. So you're taking the derivative of that squaring function first, so you get 2 times sine of x times the derivative of the inside, which is cosine of x. Okay, so that's low d high minus high d low, all over low low. So we're going to have 2 squared, which is 4, times 1 plus sine squared x, quantity squared. And they want parentheses around sine. I'm really not sure what they mean by that. Wonder if they want this. They say the argument of sine, but I'm like, maybe they mean like that. I don't think it's necessary. I think it's overkill, to be honest. But this is actually 2 sine of x. Cosine of x is another sine squared, or sine of 2x. It's a trig identity. So we could actually just square that. Put that 2 out front. So this is what we have here. And we see that the second derivative is 0 at that x value. And then the second derivative is positive from there to there. So the graph is concave upward until we get to these x values. And then it's concave downward from that x value to the next 0 of the second derivative. So if we want to, we could find those zeros, just approximate them by reading the graph. We could set this equal to 0 and solve for x, but it's a little bit of a pain, isn't it? So I'm just going to read the graph to get those x values. I'll call that first 0 x sub 1. So that's negative 0.61548. And I want to evaluate f double prime at that x value. So we see that the second derivative is 0 there. Let's evaluate the original function at that x value as well. And I'll graph it in the same color as the graph itself. And then the other point of inflection, because of symmetry, is at the same x value but positive. So I'm going to let x2 equal -1 times x sub 1. And then we will plot those points. Here's f at x sub 2. Make it orange because the original graph is orange. And then let's plot the second derivative at that x value. Yeah, this graph is way too busy right now. So let's not label that point. Maybe let's get rid of the second derivative and the points on the second derivative graph. But we see those 2 points of inflection. And that pattern repeats every 2 pi. So the next x value, the next point of inflection, would come from taking this x value, or actually repeats every pi units. We can see that it repeats every pi. So we would just take this x value and then add pi to it. Because our function is periodic. And then we can also take x2 and add pi to it. And that'll lead to another point of inflection. We shouldn't label all of those. But hopefully you can see it now. On this interval, from this point of inflection to this one, the graph is concave down. Then from here to here, the graph is concave upward. Then from there to there, the graph is concave downward. Then from there to there, it's concave upward, and so on. If you graph that second derivative on the same screen, you can see the second derivative is 0 at the points of inflection. Second derivative is positive where the graph is concave upward. The second derivative is negative where the graph is concave downward. And that pattern repeats. Oops. And if you look at the tangent line now, that was one of the things that they were asking us originally, was to graph that tangent line. Here's the tangent line. Here's the point of interest. Let's label it. And let's let that slider move. We see that the slope is 0 there, and then the slope starts to increase, and then it reaches a maximum at that x value. And the derivative graph is that teal one. And then the graph or the derivative starts to decrease. So it's still got a positive slope, but that positive slope is decreasing, and then the positive slope is eventually 0. When that slope is increasing, the graph is concave upward. When the slope is decreasing, the graph is concave downward. And where it changes from the slope increasing to the slope decreasing, that's our point of inflection. So you notice that that point of inflection corresponds to a relative maximum of the derivative graph. And of course, the point where the graph of the original function goes from concave upward and concave downward. Now, if we let that x value continue to increase, here the slopes go from 0 to negative values. So the slopes are decreasing. The graph is getting increasingly steep, but more and more negative for the slope. And then we have sort of a or maximum magnitude, a negative slope here at this value. So our derivative reaches a relative minimum. And then the slopes start to increase again. They're still negative, but they're getting less and less negative until they get to 0. And then we repeat that pattern again. And so we can see that relationship between the slopes of the tangent line and the y values on the derivative graph. We can also see that relationship between that derivative and the second derivative if we graph that, and then the concavity of the original graph and the zeros and function values of the second derivative graph. So I think that's pretty cool. Neat graph. Hope you like it. I hope you find it interesting. I think it's cool. I think it's pretty. So there's our original graph. And I'll get rid of those points of inflection now. but we have infinitely many points of inflection, infinitely many minima and maxima. But it's just a pattern that repeats over and over again. And the tangent line looks like that. It's just given by y equals the y value at x naught plus the slope at x naught times x minus x naught.